The screen is visible. Can we start now? Actually, my voice is a little bit low due to the cold. So I will go very slow by slow. So can we start now? Ella? Hello, hello.
Hello?
Yes, 2 minutes, 2 minutes. Just coming back. Hello. 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 So good morning, everyone. So let's start today's lecture. My voice is little bit low due to the cold. So today we'll discuss about the system integration and implementation of high payload autonomous mobile robot. The HMR which you have seen in various slides, how it is integrated and what's the motivation behind developing this big HAMR. So the today's outline presentation is motivation of our study, related market review of the HAMR, hardware design, mechatronic system design of HAMR, FEM analysis of hardware component of the chassis, software design, how we have integrated various sensors to this HAMR, then physical demonstration. So the motivation starts from lifting of high payload application. So we have to lift very high payload. For example, from 50 kilograms to 70 kilograms. Whenever there is a scenario of lifting high payload, generally the autonomous mobile robots are used for the rails, which is shown in the picture. We use various rail guides, which is shown in the picture, which uses a high payload automation from one place to another. But the problem is the repetitive work and the large workpiece. We use conveyor belts, traditional cranes, or the rails. But it's the we cannot get the flexibility or the fixed production. We cannot move it from one place to another. So this is the problem which we have identified. So for this, we want to develop an autonomous mobile robot like AMR, which can shift high payload from one place to another. So it will be easy to set up and maintain, and it has also some like a traditional guided robot. It has a lack of flexibility and single function. If we can use this type of robot, that is easy to set up and maintain, but there is a lack of flexibility and single function. So in order to cope up this both the problems, we want an AGV which can install and robotic arms together. So we have done some market review which are similar type of robots available in the market. So we have seen that there are many robots which are available in the market which have an AGV hosting and robotic arm on the AGV. So, but we have seen that the market is lacking with 50 to 100 kilograms of mobile manipulation robot. So this market lacks is a motivation for our study. So we have started developing a basic AGV which can host this whole component together. So we have placed 3700 watt brushless motor which can produce a torque of 120 Newton meter and use the 4 Magnum wheels which gives the flexibility to move in a omnidirectional movement. Then we combine this chassis or a small AGV together with a small KUKA KR702100 robotic arm which have a loading capacity of 70 kilogram and a power consumption of 7000 watt with a maximum speed of 2.5 meter per second. We also integrated some sensors for the accuracy and movement of these AGV to the industrial environment. Uses IMU with accuracy of 0.5 degree and sampling rate of 300 megawatts hertz. Uses a 2D LiDAR with accuracy of zero point 0.1 and a sampling rate of 30 hertz. Due to some financial concern, we don't use the 3D LiDAR, but in future we can install 3D LiDAR in this HAMR. We also use an industrial PC of 8 core with 16 GB RAM. So all these sensors are like a multiple sensors together in a one component. So this was our total structural design. So it houses a bearing, a rubber coupling here, and a bearing which is static load of 23.2 kilonewton and a related dynamic load of 25.1 kilonewton. So you can see that we houses two bearings on all the four wheels, and we also provide a rubber coupler which hosts with the motor, and there is a single phase DC to AC inverter which houses 8000 which provides the maximum power of 8000 watt. So these inverter actually provides the power to the motor by converting the DC power from the battery to the alternating current AC power to the motor. All this body hosts the lithium ion battery, which capacity of 1440 watt hour, which hosts around, you can see that 1, 2, 3, 4, 5, 8 batteries, which can sustain this HAMR for around 30 minutes. The robotic arm control box is hosted at the side in order to balance whole component and sustain the center of gravity of the AGV. The gearbox is placed here, which have a reduction ratio of 1:10, and the brushless motor, which already I told you that with power of 3700 watt and a maximum rotational speed of 3000 RPM and with a maximum torque of 33.5 Newton meter. So this is the basic layout which all the components and its capacity of designing an HAMR. Now I will discuss you any doubt on this part. Basically, we have designed initial stage, we have designed the chassis, and we have designed the chassis according to the hosting the KUKA KR770 R100 robotic arm. So the chassis was strong enough to host this arm. Then we have placed all the components. We have examined each and every part, its weight, so that the chassis can host all these components together. Now comes to mechatronic system design of HAMR. Initially, all these batteries, which is of 48-volt lithium ion battery of maximum current is 50 ampere. We have 8 batteries placed on the HAMR, is connected with a bus bar, and we place the emergency buttons on this bus bar with a no fuse breaker. These emergency buttons are, if in case of any emergency, we can just stop this button so that the HMR will go or stop. These DC motors will power all the motor drivers through the motor drivers 3700 brushless motors. So this battery has to power all these brushless motors. Then from this bus bar, we give the power towards all the sensors and IPC connected to the HMR. Then on another line for the power to the KUKA robotic arm, we have placed the inverter of 48 volt and the 12 volt. Through this, it is converted into the AC 380 volt and a 25 no fuse breaker, which can power directly towards the KUKA KR70 2100 robotic arm. And the switch is connected directly with the no fuse breaker to the robotic arm and towards the brushless motor. So this is our mechatronic system connection design of the HAMR. Now I will show you the inverter control panel, the motor control panel, and the computer display. So this is here we have placed the inverter control panel, which gives the power output status of the motor given to the brushless motors uh, given to the robotic KUKA arm, and here is the motor control panel where we can start and stop all the motors together. And here is the computer display, which gives you the output of like whatever program you want to install and how the program is running. You can see in this display. Here we can see the motor control panel where we can see all the lights green and red. If there is anything problem as in the system, there will be a red line so that we have to rectify the problem in all the motors. So this is the motor control panel of the HMR. Now this was your mechatronics system design which we have designed for HMR. Then we have done the finite element analysis for the HMR components bytes with its weight. We can see that the chassis weights of 200 kilogram. The motor is of 75 kilogram each with the four motors hosted. Total weight is of 300 kilogram. The motor driver is of 5.4 kilograms. The total weight is of 21.6. The wheel is of 75 kilogram. We have four number of wheels. So total is 300 kilogram. The chassis plate is of 5.6 kilogram. We have two chassis plates stick together. So it's 11.2. The robotic arm is of 550 kilogram. The robot controller is of 150 kilogram. We have a 8 batteries weighted 13 kilogram. We have three inverters weighted 18 kilograms. So the total weight of the component is HMR is 1690 kilograms. So for simplification of the FEA analysis, we simplify overall structure into a square and cuboid type of structure, and to simplify this curvatures and make the FEA analysis in a simple mode. For the FEA analysis, we make some FEM mesh settings. For the robotic arm is zero point 0.1 or mesh size. Robotic arm controller is zero point 0.1. Battery is 0.05. Inverter is 0.05. The plates is 0.005. And the bearing of 0.002 to perform these FEM analysis. The mesh size of other parts are fixed size, so the changes in the mesh size of the chassis respectively. If this mesh size we have already set, so the chassis, if any changes in the chassis, the mesh size of the fixed size can be changed. Also, it is hard to determine the optimized size of the mesh. Large mesh size leads to inaccurate results. If we make the mesh size very high, so the results are very inaccurate, and the small mesh size also consume more computational resources. If I make the mesh size in the small, so the computer resources will be very high. So we have done the optimization for the mesh size. So you can see the total deformation when there is element size of very high, the deformation is high. So we have optimized these mesh settings. In order to perform and confirm the effect of supporting wheels, we test 4 support wheels and also place these support wheels in different distance. Already we have seen that the support wheels is not doing good because it is rubbing up the floor. So already we have discussed that someone can do the project on this. So we made these support wheels in a different distance and check that whether the feasibility is there. So the result shows that the 4 support wheel in the middle of the beam gives the best mechanical property. So we first mounted one wheel and the total deformation is 1.648 millimeter and the von Mises stress is 174. So we placed 2 wheels. We placed 4 wheels far from the center. We placed 4 wheels in the middle of the center. We placed 4 wheels close to the center. So we have seen that the 4 wheels at the middle of the center gives the lower deformation and the best mechanical property. So it was tested on the FE analysis where to place these 4 wheels. So now we have analysis the chassis for total deformation and von Mises. So FEM reveals that the chassis with 4 support wheels has a better performance than without supporting wheels, and the safety factor is 2.713 and 7.495 respectively. So we have seen that the without wheel, the safety factor is 2.713, and by importing the wheels or with wheel, the safety factor is increasing by 3 times. So the support wheels plays an important role for increasing the safety factor. The next mass is the transmission shaft, because the transmission shaft plays an important role for the vehicle propulsion and during high stress. So we have done the FEM analysis for individual due to its compact size. Here we have checked its safety factor for the transmission shaft. An FEA analysis shows that The transmission shaft made by mud carbon steel S45C are sufficient for HMR and its safety factor is 3.65. So we have done the FE analysis for transmission shaft. So after this, you can see that the final assembly has been done, which an overall height of is of 1690 millimeter. The width is of 70 millimeter, and the length is of 2090 mm. So after hosting all the components, you can see this is the phase of the control panel box where houses the motor control panel, the inverter control panels. Here we can see that the no fuse breaker, inverter 1, inverter 2 is hosted here, inverter 3 is the hosted here. So there are three inverters, and the total battery 1 and 2 is hosted on the top of the battery 3 5, battery 6 to 8 is hosted here. So all these components are hosted properly to assign the center of gravity of the whole HAMR. And we have placed the 2D LiDAR here, and the IMU sensor, and an industrial PC. Now we have combined a robotic arm combination with ROS. So the industrial PC is connected to the robot controller through RJ45 TCP/IP protocol, and it's connected with X29 connector to the of the robotic arm. So this protocol of ROS server, which hosts these all sensors, gives the ROS topic and published to the ROS model through the SLAM. So the ROS node gives the top command to the IPC, and IPC will control the controller, and controller will gives the commands to the robotic arm. So there is a multi-thread processing, which the subscribe topic is like arm command, wait for the command for another program, and the arm will receive the command, and the axis angle exceeds limitation. If the axis angle limited action, then command will send back so that it will rectify its error and redo the command. So in this way, this is called a multi-thread processing in order to have a safety. So when a new message is received, the IPC will send this message to the ARM controller, and the controller sends moving to the command, and the encoders will give a feedback to the controller, and it receives the current coordinate from the controller and update the ROS. So your current coordinate with all the sensors will update it in the ROS, and if there is any error or any overseeding, it will look and redirect it. Now the robotic sensors are integrated like we have why we have used the two different IMU and LiDAR together. We want to experiment it with multiple sensors. So there is a Modbus TCP gateway connected with the RJ45 to the industrial PC. All these sensors are integrated through the industrial PC. The sensors are placed according to the sensor coordinate system. Like this is the G direction, X direction, and Y direction. So, so here we have hosted the LiDAR and IMU, which is linked with the base. There are two IMUs, which is linked to the center of the robotic arm. Here you can see the raw SLAM mapping of robotic arm. So you can see that the ROS and the LiDAR has created the map of the area. Now you can see the physical demonstration of the complete HAMR. This was first initially placed in our laboratory. Then it is shifted to the Industry 4.0 due to the space constraint. So this was the demonstration for an high payload manipulation robot. That's why we make it as a manipulation robot, because it's not an AMR, it's not an AGV. Actually, it's an combination of AGV with a robotic arm. So it's an mobile manipulation robot, like called as a MAMR. So this study actually develops a novel design with high payload capacity in a omnidirectional movement, which can host of 70 kg lifting capacity. It implements various control system and mechatronic designs within the ROS system for future scalability. The FEM analysis confirming that the chassis has a safety factor of 7.45 and the transmission shaft has a safety factor of 3.656, ensuring suitability for high payload tasks. The integration of sensors including LiDAR, IMU for geometric insights, and map creation through SLAM algorithm. Potential future work is involving cyber physical system into ROS using LiDAR, RBGD camera, and established digital safety fence employing high payload manipulation accuracy. So this system is very tough because we had a good safety factor for ensuring high payload tasks. So this was my experience for this HAM. Any questions?
No.
Okay. Now let's come to the another AMR which you have seen. It's an autonomous mobile robot for roll-to-roll inspection line of flexible printed circuit board. So in this, we have design and chassis layer, then application layer design, and the application structure analysis, then the schematic diagram of control software architecture of OAMR, then we have placed the gripper position control. So we have designed the Magnum wheel and its placement on the chassis for the different degrees of freedom for a vehicle. So this is our chassis layer. Initially, we have developed the chassis layer, which can gives a different movement so that omnidirectional movement can be done. So it's a left, right, turn left, forward and backward. So this is a 3D view of a chassis design. Here we have you can see that we have provided the internal view where the Magnum wheels is placed. Four Magnum wheel is placed on both the sides. It houses a 52-volt lithium ion battery, and the chassis is made of carbon steel of S45C, is similar to the same which is made in the last HAMR. We have a 48-volt power switching mode. The operation voltage is 48 volt, and the total weight of the chassis is 164 kilogram, and the size of the chassis in a height is 500 mm, length is 900 mm, and the width is 820 mm. For the application layer, we want to provide a very robust mechanism which can host the cylinder, the flexible circuit board cylinders weighted up to 40 kilograms. So we have used a C7 ball screw lid, a pitch 10 mm. The motor torque is calculated as 1.194 Newton meter, and the platform motor torque is calculated using this pitch screw and the lead screw as 1.144 Newton meter. Now this is the 3D view of an application layer which is hosted on the mobile AGV. The total weight is of 70.6 kilogram, and the loading capacity is of 20 kilogram. We made the application layer which can host the loading capacity up to 20 kilogram. You can see there is an electronic skin and a linear guideway which gives to and fro motion to put these flexible circuit board rolls to the machine, and after taking back from the machine to the rack provided, there is a four ball screw and a linear bushing, two ball screw and a linear bushing, which can move it up and down. Whole this plate can be moved up and down, and the linear guideway to and fro. FEA analysis has been done for the platform using von Mises stress, and we also done the maximum principal stress theory for this plate. You can see that total deformation will occur on the this place where the linear guideway is hosted. For the telescopic arm body, we also done the von Mises stress analysis. And the result shows that the application layer have a total deformation of 0.084255 and a safety factor of 30.636. So the application layer is made so hard that the safety factor is of 30.636. So it's not necessary to have a this much high safety factor. Maybe we can reduce some structural components or weight of the components in order to get the low safety factor, or this application layer can be used for high payload. Maybe it's from 20 kg was our target, but it can be used for 40 kilograms. And the arm body has a safety factor of 7.722. So we have used the two control software architecture of the OMR is designed according to the hardware structure. So there is a position layer which is mapped with secondary positioning, localization, SLAM, and mapping. And this position layer is of two-way because we have to move the HAMR, which have to move the OAMR, the chassis in a different way to get to the position, and also we have to move the application layer to hold the flexible circuit boards. So for this gripper position control architecture, use JSDT1 6D4 servo drive, which can offer scan, open, and RS485 communication interface with communication protocols, including AS2 and RTU as selected options. To ensure the consistency in communication protocol, according to the system, we utilize RS485 to Ethernet converter, enabling us to control the servo motors via TCP commands. So to control the architecture, we use TCP and RTU. Also, we have integrated the system safety in this, which is not shown in the slides, where we have tried some debugging of, like, if you want to control it from a remote place, we can control it with the safety features. The chassis layer and application layer uses Raspberry Pi for the lock of control features. This is due to the, you can see the symbol. This Raspberry Pi is used for as a mediating device for making it secure. With this, we can control the I/O, and if any other person wants to control it, cannot be done, as this safety feature has been incorporated in between the chassis and application layer. So here we have used a touch screen on the system with the connected with the industrial PC. We integrated camera, IMU, and LiDAR together with the industrial PC, similar to HAMR. In the HAMR, we have not integrated the camera initially, but in this case, we have used the camera because we want to run it using the gesture commands. The integration of OMR within the factory environment, its operation is manipulating cylindrical FPC boards and transporting them to material area to PCB design. The HMR has to go to the material area, then pick up the material, then go to the point 2, put the material into the PCB design, PCB machine for inspection, and wait there for the instructions. So this was our manipulation process in the factory environment. You can see the real time. You can see the movement of the HMR placing the FCV boards to the inspection machine. So that was the experience towards the towards the other HMR, other the OAMR, which was developed in our laboratory for AOI inspection. So this was the two different HAMRs, and different analysis has been done on this HAMR, which I want to share with you. Any question on these two different mobile robots?
Any questions? No?
So that was all for this class today. Thank you.
Okay, thank you.
Thank you, Ella. Ella, you can share for the attendance.
Yeah, for the PPT. Thank you.
Yeah, okay, thank you.